This is part 2 of a series on artificial neural network. In this video, we will look at the operation of ANN and its objective function. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. In the last video, we looked at the basic structure of ANN. In this video, we will see how ANN works. We will look at the ANN's training process later and look at the prediction process first. And let's look at the objective function used in the training process. Mean squared error, binary cross entropy, and cross entropy are used as the objective functions of ANN. Now let's look at the operations of ANN. There are two main steps in the operation of ANN, forward propagation and back propagation. The ANN training process requires both steps, but the prediction process only requires the forward propagation step. Here we will look at the prediction process, forward propagation. Once ANN training is complete, WBH, WO, and BO are determined. And the network is ready to make predictions. Let's take an example of a network trained on the data below. Binary classification was performed on this data. This ANN has an input layer, a hidden layer, and an output layer. Since the number of features in the data is 2, there are also 2 neurons in the input layer. And since the target value of the data is 0 or 1, there is only 1 neuron in the output layer. The number of neurons in the hidden layer is a kind of hyperparameter. Here we used 4. The feature of the training data is matrix X, and the order of matrix X is n by 2. N is the number of data points, and 2 is the number of features. The target data is matrix Y, and the order of matrix Y is n by 1. Now let's see what happens when we feed matrix X into this ANN. The connection between the input layer and the hidden layer is the matrix WH. The number of neurons in the input layer is 2, and the number of neurons in the hidden layer is 4. So W is a 2 by 4 matrix, and the bias matrix BH is connected to the neurons in the hidden layer. The order of matrix BH is 1 by 4. The connection between the hidden layer and the output layer is the matrix WO. The number of neurons in the hidden layer is 4, and the number of neurons in the output layer is 1. So WO is a 4 by 1 matrix. Let's assume that this ANN has already been trained and WH, BH, WO, and BO have all been determined. We will use the ReLU activation function for the neurons in the hidden layer. Since the target value of the data is 0 or 1, the output of this network must also be a value between 0 and 1. Therefore, the neurons in the output layer use a sigmoid activation function. Now let's input the feature data, matrix X, into this neural network. Matrix X is multiplied by matrix W8. The order of matrix X is n by 2, and the order of matrix WH is 2 by 4. So, the order of the matrix XWH, which is the product of X and WH, is going to be n by 4. Then a bias matrix BH is added to the resulting matrix. The order of matrix BH is 1 by 4, and matrix broadcasting occurs. The order of the resulting matrix is n by 4. And when the activation function of the hidden layer is applied to this resulting matrix, it becomes matrix H, which are the outputs of the neurons in the hidden layer. And matrix H is multiplied by matrix WO. The order of matrix H is n by 4. The order of matrix WO is 4 by 1. The result will be a n by 1 matrix. The bias matrix BO is added here. By applying the activation function of the output layer to this resulting matrix, this becomes the final output of the neural network, Y hat. The order of matrix Y hat is n by 1. This matches the order of matrix Y, which is the actual target of the data. Y hat is the prediction of the target value of this data. Now let's implement this process in code. Write a function to find the value of ReLU, the activation function of the hidden layer. Then write a function to find the value of sigmoid, the activation function of the output layer. We define the input data X, and let's assume that we already know the parameter matrices of the neural network, WBH, WO, and BO. Then the Y hat can be calculated like this. This is the final output of this neural network. The elements of the Y-pred matrix are as follows. These elements are the values of the sigmoid function, representing the probability that Y is 1. If this value is greater than 0.5, it is defined as class 1. Otherwise, it is defined as class 0. And the actual target value Y is as follows. Comparing the two results, they match exactly. In other words, the accuracy of this neural network is 100%. This is the forward propagation and prediction process of the neural network. The previous page assumed that we knew all the parameters of this neural network. These parameters must be determined through a training process. In order to train an ANN, a loss function, which is the objective function, is needed. In regression, mean squared error is used as a loss function. And in binary classification, binary cross-entropy is used. And in multiclass classification, cross-entropy is used as the loss function. Regression uses a linear activation function for the neurons in the output layer. And binary classification uses a sigmoid activation function. And multiclass classification uses a softmax activation function. Our goal is to find the parameters W and B that make the loss function as small as possible. We mathematically proved that this becomes the loss function for regression using the maximum likelihood method in this video. The binary cross-entropy was proven in this video, and the cross-entropy was proven in this video. We have two AN models A and B as follows. The class Y predicted by the model A is like this. And the class Y predicted by the model B is like this. Both results are identical. However, the MSE and BCE of model A are smaller than those of model B. This means that the model A has better performance. The accuracy of both models is 100%. but the predictions of Model B are somewhat unstable. This is because Model B predicts y hat 0.49 as class 0 and y hat 0.51 as class 1. In addition, although MSE can be used for classification, it is better to use binary cross-entropy or cross-entropy. Next, let's understand the cross-entropy from the perspective of information theory. The concept of information entropy was introduced by Claude Shannon in his 1948 paper, A Mathematical Theory of Communication, and is also known as Shannon entropy. In information theory, the entropy of a random variable is the average level of information, surprise, or uncertainty inherent in the possible outcomes of the variable. He defined the amount of information as being inversely proportional to probability, with the idea that the amount of information for high probability events is small, and the amount of information for low probability events is large. The probability of two independent events occurring simultaneously is the product of their respective probabilities. However, to calculate the total information amount of two independent events, it is reasonable to add the information amount of each event. Therefore, it makes sense to define the amount of information as the log of the inverse of probability. And the amount of information is finally defined as the average of possible events. There are two independent events A and B. The probabilities of the event occurring are PA and PB respectively. The probability of two events occurring simultaneously is PA times PB. If the amount of information is defined as 1 over P, the amount of information when two events occur simultaneously is 1 over PA times PB. In other words, it is the product of two amounts of information. This is not reasonable. It makes more sense to add the two amounts of information together. If the amount of information is defined as log 1 over P, then the amount of information when two events occur simultaneously is log 1 over P A times PB. This is log 1 over PA plus log 1 over P. That is, it is the sum of two amounts of information. This is more reasonable. Therefore, the amount of information is defined as log 1 over P. And if you calculate the average with probability P, this is the entropy. In other words, entropy refers to the average amount of information. Next, let's look at the KL divergence. KL divergence is the difference between two amounts of information. Y is the probability distribution of the actual class, and y hat is the probability distribution of the predicted class. Using Shannon's definition, the difference between these two amounts of information can be expressed as follows. The information amount of y is subtracted from the information amount of y hat, so that this difference is positive. The smaller the difference, the more similar the two distributions are. And calculating the expected value of this difference is KL divergence. This is greater than or equal to 0. This inequality is established by Gibbs inequality theorem. Now let's minimize the KL divergence with respect to y hat. The second term is independent of y hat, so we only need to minimize the first term. The results are as follows. This means that if y hat is determined to minimize this part, the distributions of y and y hat become similar, because the KL divergence becomes minimum. This means that the predicted class is closer to the actual class. This part is the cross entropy. Minimizing CE makes the distributions of y and y hat similar, so it can be used as the objective function of ANN. Finally, let's look at how quickly the classification model converges as CE decreases. According to the results below, we can see that as CE gets smaller, the predicted probability y hat gets exponentially closer to the actual probability y. Let's say the probability of the actual class y of a data point is like this. This is one hot encoded, meaning there's a 100% chance that the class is 0. And let's say the predicted probability is like this. This means that there is a 70% chance that y is class 0, a 10% chance that it is class 1, and a 20% chance that it is class 2. And the cross entropy defined on the previous page is like this. Meanwhile, Jensen's inequality for log of x looks like this. This inequality can be written as follows. The right-hand side is the negative cross entropy. Now let's look at what sigma yi times y hat I means. Multiply the probabilities y and y hat and add them up to get 0.7. This means that the probability that y hat becomes y is 0.7. Therefore, we can express this as the probability that y and y hat are the same. Then this Jensen's inequality can be written as follows. This means that the larger the negative cross entropy, i.e. the smaller the positive cross entropy, the more likely it is that y hat will be y, because the lower bound increases. This inequality can be written as follows. This means that as you make the negative cross entropy larger, that is, as you make the positive cross entropy smaller, the probability that y hat becomes y increases exponentially. Therefore, it is very reasonable to use cross entropy as the objective function in classification models. So far, we have looked at the prediction process of the ANN model and looked at the objective function to be used in training process. In the next video, we will see how to train an ANN using this objective function.